Good afternoon, everybody. My name is Svand, and I'm Simulation Product Manager in INTERCAD. And today we will go through the webinar session regarding using shell element in SolidWorks simulation. If you could please hear me, and also you can see my desktop, please say yes in a chat box. And then we can start progressing with the presentation, please. If everybody who is attending say yes, if they can hear me and they can see my screen. The chat box option. Okay. So today's topic would be regarding to solid element meshing and shell element meshing, about their definitions, options, and applications we have. We will also introducing mixed meshing, where we have solid and mesh shells are existing in a part or assembly at the same time, and also we will experience and have a bit of highlight about solid shell bounding when we're trying to connect solid and mesh elements together, and we will experience through the mesh failure diagnostic options we have in this software. Now let's start with the definition of finite element analysis. FEA is a numerical technique of solving field problem described by set of partial differential equation. So in order to do that, we have to split our actual model part or assembly to the tiny spaces called finite elements in order to represent the physical object. So this procedure is called meshing. In any FEA model, as you know, we have nodes and elements, and there are two basic assumptions we have here. First is a simplified displacement pattern is assumed for each element, and also continuity of displacement is maintained at nodes. So with these two basic assumptions, let's have a better presentation and definition about the elements and nodes. As you can see in a picture, a single element consists some dots and lines. So basically, nodes are these dots, and the connection with the nodes is called elements. We can have single element in a triangular shape with sharing its node with the other element as I'm pointing at. So what happened when we're running FEA analysis is force and displacement are calculated at nodes. Stress and strain are calculated within each element. And also interaction between the elements are via nodes, where we actually sharing nodes between the elements. Now in this regard, we can divide the elements in two main categories. First category is talking about solid elements or continuum. Or the second part or second category is considering structural elements like beam elements and shell elements. With that definition, then we will go through the options we have in SolidWorks shell and solid meshing. When you're trying to mesh a part or assembly in a SolidWorks, we have two options: going for draft quality mesh or going to high quality mesh. Draft quality mesh basically is a linear tetrahedral solid elements in a case of solid meshing, which defined by four corner nodes connected by 6 straight lines, while the triangular shell element is defining by 3 nodes and 3 straight edges for the connection. So the advantage of using these type of elements, or let's say draft quality mesh option is a very quick calculation time and get the response. However, we will compromise the accuracy of the result. As you know, we are trying to put these elements to represent the actual geometry. Since they have limited number of nodes, they are not going to fit into the actual shape, and we might miss some corners, fillets, or curve, or anything else. However, they are very good if we want to have a rough estimation about any FEA analysis on our part, or again our assembly. Compared to this, we have high quality mesh, where it is, in a case of solid elements, it's a parabolic tetrahedral solid elements, which defined by 4 corner nodes, as you can see in this shape, 1, 2, 3, 4, 6 mid nodes, 1, 2, 3, 4, 5, and 6, and 6 parabolic edges which connect all the nodes together. So parabolic triangular element is defined for solid mesh, and we have parabolic tetrahedral element, where it is 3 nodes corner, 3 nodes in mid surface, and we have 3 parabolic edges which connecting all this node together. Now the advantage of using this type of element, as they have more nodes, they are more flexible to fit into your geometry and have a good representation about the actual model you have. They can capture the boundaries more accurately, and also because we have higher degree higher order of elements here, we will have better mathematical approximations. However, we will compromise the simulation time, as it will be significantly increased, and we will require greater computational resource compared to draft quality mesh. So this is the basement we need to just recap before we are introducing shell elements. Now, the basic definition about the shell element modeling is considering that shell elements are 2D elements capable of resisting membrane and bending load. As they are 2D elements, they are naturally the first choice for any sheet metal or thin parts. If you actually model a surface without any thickness, this is the only option you have in SolidWorks or in any other sort of software. A very important note is about the degree of freedom when we have solid elements or shell element. As you can see in the picture, the degree of freedom for the for the solid elements simply is 3 translational displacements, X, Y, Z, while in shell elements we have 6 degrees of freedom, 3 translational and 3 rotational. And this is one very important note you have to always remember if you are using a mix of solid and shell elements, where in their intersection line, as the shell elements are capable of rotating, we might build up a rigid body condition or a hinge body condition, and we may produce any unrealistic displacement. Therefore, in this option, we should be very careful to bound the mesh and the nodes and make sure they are correctly connected to each other. Okay, now before we actually introducing the shell element and the techniques we can do, it's a very good idea to present that a case where we're using solid elements and get the accurate result with the solid element, then compare it the same case with the shell meshing option. Just imagine we have a pulley, let's say, part, and we would like to have an FEA analysis on the pulley. So in order to capture the stress, strain, and possibility of failure on the actual part, if we would like to perform this analysis, initially we can put some elements here, and depends on how many elements we put through the thickness, we can get different result. Let's stop this and go to a real model, which I'm now bring it on the screen, and do a real practice here. So this is the pulley part. As you can see, it's been split in half in order to minimize the simulation time. So for the first study, we would like to put a solid element mesh. So going to the tab with the simulation, you can see the solid body is active. The material being assigned as AISI 1020 steel. We have fixed the inner face to have no translational movement, and we also selecting the symmetry condition on this face. Applying the pressure of 0.2 megapascal on the face, as you can see, then we would like to request for creating a mesh. As you can see, the handle is being set in the middle of coarse and fine, where you can see curvature-based mesh option with the element size of 3.34 millimeter as maximum and minimum. Clicking OK, and you can see it's been mesh, and now we get back to the model. You can see the very important information about the mesh here. First of all, through the thickness, we have just one element. Therefore, our calculation would exist at these points, at the nodes, and any place, any other, let's say, calculation or request or probing for the result would be an interpolation between the exact values we have on the nodes and just an interpolation. Therefore, if there is any significant changes of stress happening through the thickness at somewhere in the middle, we are not able to capture it because there is no calculation point for us here. Now, the other important information, as you can see, the connectivity of the mesh is not very great, and it is a very rough estimation about the actual geometry we have. Now, the second thing I would like to grab your attention is about the running or solution time. If I click run, you can see the solution is getting finished in less than 2 seconds. By reviewing the result, we can see the maximum 1 meter stress is being reported here, and the magnitude is 81.236 megapascal. And more zoom in, you can see a very coarse transition from the back or inner surface to the other surface, and there would be a very rough interpolation of 1 meter stress here. So that will bring our attention that what we have generated here is not, first of all, that much accurate in the terms of magnitude and distribution at the same time. So we have to reconsider this analysis with higher number of elements. You can right-click on the mesh and see the details of what's been created. You can see the total node we have created is 19285, and the total element is 9528. So we will hold this and we will duplicate the same study to a new study, where this time with the same condition we go to create a mesh, and we will request a very fine mesh where the element size being reduced to 1.1 millimeter. Click OK, and now you can see it takes more time to create the mesh, and this is going to be finalized very soon. Okay, Here is the mesh representation. Now, focusing more and zoom in, you can see we have created 3 elements through the thickness, 1, 2, and 3. Therefore, we have more points for calculation through the thickness of this material, 1 on this edge, 1 on the middle, and 1 at the end. So 1, 2, 3. Therefore, anything between would be interpolated, but we have absolute values on 3 points at least. Okay? The mesh connectivity through the surfaces and the curves are presenting very fine and good. Now we request for run this time. Now I would like again to grab your attention on the simulation time. So you can see how long it's been passed, as it's 6 seconds, 7 seconds at the moment, and still the model is getting prepared. And after 12 seconds, it's getting the solution started, progressing, and it's around 20 seconds, and still we are solving the model. So 22 seconds is what we done. So in that very simple model, what we showed is from an initial estimation of 2 seconds to more accurate result, or let's say more realistic result, we are increasing our time by factor of 10. Just imagine if you have a very complex shape or a very complex assembly, and be in a right mesh alignment and orders could take a very, very considerable time if we are still with the solid elements. Now let's review the result. As you can see, the magnitude of one misses stress is being increased to 87.032 megapascal. Same location is reported, but now we can see more events happening through the thickness. So what would be the solution if we want to really avoid and really capturing the right image of the actual model, stress and strain result, if we can simply say we want 3 faces, 1 on top, 1 on bottom, and 1 in the middle, and avoid the other elements through the thickness and see the result there. That is where the shell elements application coming to the application. Now, simply comparing, we are increasing the degree of freedom, and we simply spending a lot of time for, let's say, inappropriate or unnecessary calculations, while we can have this option. By putting the shell elements on existing surface or on a sheet metal bodies, it could be on a mid-plane surface, or it could be outside or inside of the faces of solid bodies. Now, in the second part, we are going to experience this option and see how we can set it up. Back to our model here, we can simply request for a new study. Before that, we go back to the model and we will do 2 types of solid meshing. As we said, the best option is to put your surface on the middle of top and bottom and put your shell elements there. How we can do this in SolidWorks is quite easy. If you go to your menu to insert, surface, and mid surface. By clicking this option, now the software will ask you what face is your initial selection. For example, I'm selecting this. There would be a pair surface on the other side, as you can see here. You can choose the pair one yourself, or let the software to automatically find this selection and the pair for you, where at the meantime all the surfaces who are tangent to the initial one are going to be select and the pair will be fine. So basically we have a face on blue and the pair one in the pink color. The position, as you can request, is 50%, means between these two faces, and by clicking OK you will get a mid surface, and if I zoom you can see the blue line on the face, and this is the surface being created at the middle of top and bottom faces. Alright, so we have created a middle surface here in order to put the shell elements on there and perform FEA analysis, and then we have the option to see the stress on the mid surface, on the top surface, and on the bottom surface without really having a lot of elements through the thickness. Now in this regard, we have to click to a new study. So we're requesting for static and clicking OK. When you're starting the new study, you can see your parts are being imported, one solid body as you can see here, and one surface body as you have created this. So we will go to exclude this solid body from the analysis, and this is what we created. You can see the surface body is here, where all the feature is being recognized, and we have the symmetry shape. So because we have put this surface on the middle of our actual part, top and bottom, by right click on this and edit definition or define shell by selected faces, we can select all the faces we have in our body, and we can assign a thickness to it, where the original thickness was 2. Now you can have the option of thin, thick, or composite material here, while again I'm repeating, this is located on the middle surface, where this option is going to be present and explained in this slide. You have to choose the thin option based on Kirchhoff theory, where span size ratio through the thickness is more than 20. For instance, in our case, the diameter over the thickness ratio should be more than 20 if we're choosing the thin option and putting the thickness for it. In this case, thin shell element, ignore the shear deformation through the thickness of the shell, and as you can see, tau is 0. But at the meantime, if the ratio of span through the thickness is somewhere between 10 and 20, you have to choose the thick option, where the mid plane will have a constant shear deformation, and that should be considered based on Mendelin theory. So back to our model, and you can see here we have thin as the diameter ratio over the thickness is more than 20, and simply we selected the face, we put the thickness, and because it's located at the mid plane, then simply we click OK, and we have simply defined our mid surface shell elements. Okay, so bringing the same fixtures as mid surface is being fixed, we have symmetrical, let's say, condition on the edges this time, assigning the correct material, and now we're requesting for mesh, where this time, as the model size been considerably reduced, then we can simply ask for mesh controls. If I show you, this is the face we request the mesh to be finer, where the element size are 1.5 millimeter with a growth ratio of 1.5, and also the general setting for the mesh is set up to a curvature base with the element size of 4.64 as a maximum and minimum one. So creating the mesh, and you can see what is the result. Mesh being created, as it is a surface, we have finer mesh here, and a very, very important feature, as you can see here. We have the outer face of the actual model colored by orange color, and the inner face is yellow, gray. So here is where the shell elements are located. So the orange color is showing you where the shell elements are located, and if you like to double confirm, you can right click on mesh and ask for render shell thickness in 3D. It will do a virtual thickness for you and showing you where it is located. You always have the option of changing your shell elements to be in inner face by selecting a face, make it active, go to mesh and flip shell element. As you can see, this face is being transferred to the inner side. We can undo this by again say flip shell element, but very important note here is when you flipping your shell, you should be aware of very important factor that all shells should be connected to each other on the same, let's say, orientation. So if we want to flip all this, you can simply right click, select the tangency, means all the faces are now being selected, and then go to mesh and then ask for flip the shell elements. Now you can see these elements or shell elements being transferred to inner side. All right, now we have created our shell elements based on the mid surface. Well, we created on our model section. The boundary conditions are now being fully set. Thickness and material is being set. Now we can run the result. So again, 2 seconds, and now we are going to experience the options we have to show the stress. If you right click on the stress and edit definition, you can see the property we're showing or the component we're showing is 1 Mrs. in megapascal. Now if you just open up this dialog where you want to present this, you have the option of top, bottom, membrane and bending. So if you show the 1 Mrs. on the top and click OK, you can see 80.397 megapascal is being reported on the top face, where if we requesting for bottom face, this magnitude is 64, and if we just asking for membrane, it is 13.558 megapascal, and if we just asking for bending, it is 72.044 megapascal. So simply, we have put our shell elements somewhere in middle, and the software calculated the stress values on that face, top face, bottom face, and calculated the bending for us. So this is instead of having 3D elements all going through the bodies and probe the result and make unnecessary refinement to capture the events through the thickness. So 2 seconds and fairly the same option and same result. So one very important note when you're performing these tasks is you have to make sure that you have putting all your mesh, if I show it again, in a right order and they are connected, as we have a continuous result of stress over the surface. Now the question would be, Alright, this is a very symmetrical shape, and you can simply put your make the mid-plane surface quite easily. What if I have a very complex assembly and I'm not able to use that mid-plane surface location? Is it possible to select any face on out or in, assign the shell elements, and then tell the software it is on top and you have to offset it? Then yes, the answer is yes, and we can do this by offsetting the shell option while you defining the thickness. For this purpose, I have created a new study where you can see we can define our shell on any face if you like. Bring the solid body and simply click on a face and say define shell by selected faces. So we can simply saying, okay, this is my solid body, I'm choosing the top one and this one and this one and other faces all here I have. Now I would like to say the thickness is 2, but one important thing I would like to mention, these faces that I have selected are located at top. Therefore, there is an offset option here for you where you can tell the software the faces you have selected are located on the middle surface of your actual part, or you can tell it is on the top face. If you select this, the software will automatically offset your faces by a factor of 0.5 or 50% to locate them on the middle surface. If you're saying it is on bottom, there would be a minus 0.5. Or if it's an irregular type, you can specify how much offset you really required. So go to edit definition about what I have created before. You can see this is the surface to be located on the middle plane. So we can request this applying the same fixtures and applying the same sort of force to this model. Request for mesh, I can show you the mesh, which is purely connected, and then request for run. Before we made the run, there would be a very important notice here. So this is what we actually explain now, where if you selecting the mid plane and you offset by 0.5 or minus 0.5, then this is how you create. But a very important note is going to be here, as if the parts or the assemblies in the parts, they have different thickness, we have to make sure the shell mesh are aligned correctly. A very good example of this is showing as a simple example here. Just imagine we have a metal stripe and we incorrectly put the shell elements in the middle, on the first half on the top and the second half on the bottom. As this is completely explaining what happening if you fix that edge and apply the load, the stress value are going to be average from what is happening on the left side and the right side, and you can see you have a 0 stress at here, which is absolutely wrong. So we have to be very, very careful if we manually select the faces and trying to offset the shells, make sure they are all aligned. Otherwise, this is the possible scenario you will get on. So we need to be very aware of this fact and make sure the mesh aligned correctly. All right, now let's get back and review what we have here. You can see the shell elements are simply aligned. We have requested the thickness to be in the middle, and then we can run the result. Again, around 2 seconds with a very good fine mesh. So we made the mesh finer, and now we can review our stress result here. Where it's showing, currently it's showing 83.073 megapascal as the maximum one, where you can see it here. We can alter or switch to the bottom one and see the other value. We can also see the membrane, what is happening in the middle, and if we request for bending, this is the representation. Okay, so this is showing us all the layers which we required to analyze this part through its thickness, considering stress, strain, or any other magnitude. You can always switch between 1 Mrs, normal stress, principal stress, or again back to 1 Mrs stress. When you're showing this, you can also tick the render shell thickness in 3D and click OK. It will show you the result through the 3D representation anytime you like. Or if you just click it off and show as a tensor plot, it will show you the actual vectors you have and tensors you have through the whole model. You can play with the true scale deformation or automatic option and make customize, let's say, presentation of the stress values at any stage if you need it. All right, and also you have different options like displacement can be shown, strain value can be shown, and at any time if you like to make a user-defined or tailor-made type of stress or have different type of stress, you can right-click on the result, define safety of factor plot, stress plot, displacement plot, strain, and get the resultant force respond at any selection point or phases you like. So that is simply highlighting for us how we can accurately use the shell elements to get the stress strain value and performing FEA analysis while we avoiding a lot of time or a lot of calculation time, and still we get accurate result. So this is a very good hint for anybody who just doing an analysis with the sheet metal, pure sheet metal parts, and this will reduce the calculation time and will maintain the accuracy. Now, next thing, what if we have bulky parts where they are very suitable for solid mesh, and there are some parts like a thin parts or sheet metal parts at the same assembly? What we have to do in this case? So in SolidWorks, we have the option of getting a mixed meshing. You can simply assign solid mesh to some parts and shell elements or shell meshing strategy to the thin features you have. But before doing this, again, I'm grabbing your attention to a very important note. Imagine the example of a thick plate and a thin plate attaching to each other, and we're requesting for solid mesh on that one and shell mesh on the thin parts, where we explained it before, as the shell elements have 6 degrees of freedom, and now the measure tool have to translate the mesh from the surface and connect this to the solid mesh on the other surface, it should be fully compatible and the nodes are attached to each other. Otherwise, if it's not happening, we may introduce a rigid body mode if we don't handle this appropriately. So we always make sure we have a compatible mesh at the interface. If we get incompatible mesh at the surface, then we have to go and generate a bond contact on that intersection where it is simply attaching the mesh through the intersection. In any type, we have a mesh diagnosis tool. If we have any problem with the meshing, we simply go and check with that measure tool, and I can show you where you can check this. If we click on mesh, failure and diagnosis, it will bring you the communication box, and while performing the mesh, if you have any problem of compatibility and let's say connectivity of your solid and shell elements, it will appear here. You have to simply go back to your component contacts, add a contact set, and make sure they are fully connected to each other. So that's all about the presentation today, and I would like to thank everybody for listening, and I hope it's been useful for you. As you can see, my email address is here. If you have any inquiries, please send me an email.